Hello everyone, and welcome to my talk about Favour, which is a collaboration between the Pandora team and the machine learning efficiency team. In particular, it's by me, Thomas Ehle, Sahar Karimi, and Peter Tang. Favour is an acronym for Fast Variance Operator for Uncertainty Rating. But what is an uncertainty rating, and why do we need it? So let me present an example from a real collaboration between the Pandora and the business integrity team. This is work started by Ashan, which has been used in production today. Say Ashan here, for example, has an ad he wants to run on Facebook. Business integrity needs to figure out whether it conforms to the community standards. So they run a machine learning model on the picture. In a standard machine learning model, we'd have a classifier that decides whether the ads follow our integrity guidelines or not. Of course, the model may make mistakes and people could get angry. That's why we want people in the loop who can hopefully judge and make the right decisions. But the humans can't look at all the ads. So we need a system that can express its own uncertainty. Then we can send the corner cases to the humans and automate the rest. Of course, the standard machine learning models also tend to give an uncertainty score, but it's not very well calibrated, which is something I'll talk about later. And this lack of calibration means that the wrong ads might get sent to the judges, and so we waste our human capacity. So the main goal of this is to have machine learning models that have a better and more principled understanding of their own uncertainty. But wait, let me show you what I mean by calibration. So there can be multiple ways a machine learning model can be uncalibrated. In these graphs, we see three models trying to learn the same sign function. The data has some noise added as well, which we would like to understand. In particular, we want the model to create a confidence interval around its predictions. This confidence interval should be precise in the sense that a 95% confidence interval should contain the true label in 95% of the test cases. In the first graph, we see that too many points are outside the 95 confidence interval. We say that the model is overconfident since it failed to appreciate the amount of noise in the data. The middle model is underconfident. It's afraid of the noise and makes really wide confidence intervals just in case. The final model is well calibrated and around 95% of the points are inside the confidence interval. So we generalize this from just being about 95% confidence intervals to being sort of an average or all confidence intervals. To understand this calibration graph, maybe look at the first one up here, the average calibration, and then look at the x-axis called predicted proportion and interval. Maybe look at it at around 90%. You'll see that the x-axis at 90 corresponds to y-axis at 0.6, which is the observed number of points in the interval. So it widely overestimates how many points will be in this interval everywhere, which is the underconfident model. The opposite pattern here is in the underconfident model, and again, the well-calibrated model. Here it turns out to be well-calibrated at all the different intervals, and so get a nice straight line. In general, our goal for well-calibrated models is to see something like the upper right corner, where the blue area, also known as the expected calibration error, is really small. I should just say something about uncertainty because it confused me in the beginning, and that is that we have multiple kinds of uncertainty in these kind of systems. What's particularly useful about these probabilistic neural networks is that they can give us an idea about epistemic uncertainty. If you look at this picture, you have the outcomes of a three-class prediction. In the first picture, we have a clear, certain prediction. It says this data belongs to class 3. In the second picture, we have a typical uncertain prediction where the model feels like the input belongs evenly on all classes. It's some sort of mix. This data maybe could be like half dog, half cat, who knows. But then the last picture shows a model that's honestly very uncertain. It says, well, it could be that it belongs to one of the classes. It could be that it's a mix. I really don't know. The model is out of its regions of expertise. This is the type of outcome that you can only really get with these probabilistic neural networks and doesn't exist in the classic frequentist ones. So how does this work? Do we have to go to, Bayes and the whole framework for reasoning about epistemic uncertainty? Well, there are two schools of thoughts about this. And to make things simple, I'm just going to do the easy one based on dropout. I hope this doesn't get me kicked out of probability. Okay, here we have a simple probabilistic MLP based on this dropout technique. So you see here we have point here in the beginning, there's actually like 7 points on top of each other, but we just copied it. Then we're sending it through this dropout layer, just a simple linear layer with dropout. For each of the points, we sample the dropouts differently, so the outputs here will be slightly different. We do this again multiple times, and every time so the divergence grows. And then at the end, we can measure how different they are. The idea is that the model was trained using dropout, so it has learned to compensate for only having a random subset of its weights applied. However, when given inputs that it doesn't understand, perhaps they're very different from what it saw during training, it fails to compensate and the outputs start to drift apart. Of course, we don't really want to use too many points, because if you use 7 points, that means your inference times will be 7 times slower. And this was the original reason why Pandora and machine learning efficiency started to work together on this, that many XFN customers, they wanted to use these sort of models, but they could only allow maybe a factor 2 or 10% maybe even slowdown. So these 7 times slowdown, it's not really great. The idea of Favour was that since we're only looking at a small set of samples, we can't expect it to represent more than the first and maybe the second moment of the underlying distribution. So what if we just replace the samples with some sort of simple distribution, like a Gaussian that has the same moments? This even has the benefit that we don't have to measure the points in the end, because we just get distribution outputted directly. So here we trained a neural network with dropout on the CFAR 10 dataset, where a model has to distinguish between 10 classes of pictures, like airplanes, cars, and birds and stuff. And we then here on the first plot, we have a baseline. The baseline got around 65% accuracy, which is not great, but it was a pretty simple model. And then the dashed line, that's the standard dropout Monte Carlo method, where when we give it more and more sample points, it's actually able to improve its accuracy above the baseline, which is interesting in itself. Which basically means that we were able to extract more information from the model than just running the model normally in a forward pass with dropout disabled. But we can also see that using our new method, we're actually able to achieve around the same accuracy as using lots and lots of samples. So this is a logarithmic x-axis, even with just the same amount of time as it takes to maybe push 3 samples. We can also look at the rightmost graph here, which is the calibration error we talked about earlier. This measures the blue calibration error area. And again, we see that the baseline, sort of just using these probabilities that the model outputs, we can quickly beat that in terms of calibration. But again, using this Favour method, we can achieve these nice results using much less time. All right, so the next step is getting a little bit more technical into how this Favour approach works. And at the end, I'll come back to some more results. So this idea of variance propagation, we weren't the first people to have it, but I'll explain a bit later why our method was able to actually achieve good results and useful results for the first time. But you might notice that a Gaussian distribution is completely determined by its mean and its variance matrix, where covariance matrix is defined as basically you have the individual variances for all the neurons on the diagonal, and then you have all the sort of pairwise interactions on the off diagonals. And because of this sort of correspondence, we sort of sometimes assume that the data is following a Gaussian distribution or like these distributions we're pushing through, but most of the time we don't really care what the distribution is. We just say that it's some distribution that has some mean and covariance. So how do we push something like that through a neural network? Well, it's easy if you have a linear layer. So a linear layer just means you have some weight matrix that you multiply on your vector x, and you add some bias b. And if you use sort of standard multi-dimensional variance formulas, you get that the variance of this multiplication is just the weight matrix times the covariance matrix times the transposed matrix. And similarly, we can deduce how the variances change when you use a dropout. So here you see the dropout is also a random variable, of course, because you don't know what's going to drop out. But it turns out you end up just getting the covariance matrix again, plus something added to the diagonal, where the diagonal is like the magnitudes of the inputs, the expected magnitudes, plus a factor that's proportional to how much you drop out. So, but this basically shows that if we knew the mean and the variance before, we can easily find out what they'll be after the linear layer and dropout layer. For the activation layers, it takes a little more work that we won't really go into, but you can use sort of Taylor approximations. You can use these ideas of assuming that the data was Gaussian, and And we tried various different things to figure out what gave the best practical results. Okay, so more importantly, is this actually faster? So of course, updating the covariance matrix like this is very easy to do. These activation layer things, they'll turn out to be medium, expensive. But the worst part is this thing up here. So you see that when we're doing a full matrix multiplication, normally in neural networks, we're just doing a matrix vector multiplication, which is like d squared time, if d is the number of neurons. But here, since we're doing a whole matrix multiplication, it becomes cubic. And that's pretty bad because that means we're basically spending as much time as doing the Monte Carlo sampling with d points. And I don't know, like if we could actually push d points through the network, then we could probably get a very good estimate of the covariance matrix anyway, just using that method. So we're not really winning anything. And I think that was probably the reason why these sort of methods didn't really win much. They didn't get used much in the past. But we were determined and we wanted to try and solve this problem. So we decided after some experimentation that we could actually get a really good useful estimate by not storing the whole covariance matrix. We just want to store the diagonal, which is like the real variances, plus like a low rank approximation. So we'll write the sigma in this sort of form. We'll also assume that this d thing is positive, which is of course makes sense if it's the real variances we're measuring. And this is pretty good. This is actually a really useful form for a lot of things. Like we can still sample from this compressed form without having to ever decompress it. If we just sample two random vectors like this and combine them by taking the square root of d and just using like half of this low rank approximation, we get a normal distribution that follows the real distribution if we had multiplied it out. We can even compute the inverse of this sigma without ever spending cubic time using something called the Woodbury formula, which basically ends up just computing like an inverse of like a very small matrix that sort of you flip the two low ranked ones so they don't get an outer product but like an inner product. But the main benefit is that we can now compute the products faster. We multiply the weight matrix on both sides, we split up the sum, and now we see, let's assume that our low rank matrix has dimension d. Then we have two full rank times low rank multiplications and one low rank times low rank. So this ends up being d squared r, and where we assume r is like really small, maybe like 5 or something like that. Oh yeah, so actually it's still a little bit problematic because we still have also to do this one here where we, even though we're just doing a matrix multiplication with a diagonal and then with another full size matrix multiplication, you can't actually do this fast. Even like if you can pre-process the W's, and we were looking into this, and there's no really good way to do it. Instead, the solution becomes to remind ourselves that we're not actually trying to compute this product. We're trying to compute the next diagonal plus low rank approximation to this product. And the thing is, when we're trying to make these approximations, the algorithm we're going to run, it has like this key operation it needs, which is multiplication with a vector. And we can multiply this thing on a vector really fast, because that just means you multiply one matrix, you scale everything using this diagonal matrix, and then you multiply it by another matrix. So this is just d squared time. And that's kind of the key to the whole thing. Yeah, so now we're getting into probably the most technical part. So I hope I hope you hang on. The idea is here, okay, we're going to have some matrix here, and we only really have Oracle access to it. We can just ask for a multiplication. We can't ask like what the matrix actually looks like. But we still want to compute this truncated low rank approximation of this matrix. This would at least be the simple way to do it. Like we first make a low rank approximation, and then we take the diagonal of the difference as the remaining thing. And this is like a simple algorithm that will always work. Remember, we need this d to be positive. And basically, this comes from the fact that sigma is symmetric. So you can write it as this sort of like sum of outer products with singular values. And the truncated SVD is just the first k of them. And now if we look at the diagonal, we're actually getting like a sum of square values. And because, again, the covariance matrices always have this property of being positive semi-definite, which means all the singular values are non-negative. And so the whole sort of residual diagonal here in point 2 will be positive. So this is just like a quick proof that it's actually possible to make these decompositions, but it's not actually fast enough for us still, because this one here, it requires us to compute this whole SVD computation, which can be expensive. And the other problem is that even though this creates a valid diagonal plus low rank approximation, it doesn't necessarily come up with the best one. So we looked into the research and the papers on what's called the robust principal component analysis, which is this field of compressed sensing, where they're trying to also split things into not diagonal plus low rank stuff, but into like sparse matrices and low rank matrices. And a useful technique that's used here is something called alternating projections, which is honestly like just a really cool algorithmic technique you might be able to use in lots of places, and maybe you do use it without like knowing the name. But the idea is if you have two convex sets and like just some sort of properties, and you want some data that has both properties, then by alternatingly projecting it into either of the sets, you can prove that you'll converge into something that's in the intersection of the sets, which means that you have found some point that has both of the properties you want. So basically, this is what we end up doing. We sort of iteratively run this thing, where first we try to minimize with respect to the low rank matrix by taking the SVD of the sigma minus diagonal, just assuming we have some starting point of the diagonal. Then once we have a better low rank matrix, we then minimize again this difference here with respect to the diagonal matrix. Well, yeah, we just compute the difference and then we truncate all the negative values. And we just repeat this. We'll repeat it like maybe 3 times because we are very cheap. And even like with the SVD, as I said, it's very expensive. So we actually sort of open up the singular value decomposition black box, and we take this thing called a subspace iteration that normal SVD performs like 100 times, and we just do it 1 time. And the reason that's useful is the other step in step 2. It's also very cheap, so we might as well just interleave them and spend equal amount of time on these 2 parts. Okay, so I should say that this doesn't necessarily converge always to the optimum, because sort of these restrictions, like it takes a little bit of time, but you can formulate these things as these convex, or like, no, not convex, that's the point, but these different sets that we're projecting into, but unfortunately not convex, which creates some problems. But in practice, it works very well. So in this plot here, I just like made a lot of matrices that had like a low rank part and a diagonal part, and I wanted to see if I ran this algorithm, how long would it take before the managed to completely decompose this thing again and find the optimal D and the optimal low rank part that takes the error to 0. Or in this case, I wanted to take the error to like 10 to the minus 2. And you can see that basically even for like very high dimension, it only takes like 10 iterations. And so, yeah, I guess I said before we were only using like 3 iterations, but that's because we're willing to live with an even larger error than 10 to the minus 2. Okay, so let's see some more results. So you already saw this one here on the image data set, where the x-axis here is the number of seconds that it took for the 2 different algorithms. Like when they were just given for the sampling method, we allowed it to use more and more samples, and for our method, we allowed it to use a higher rank approximation for the low rank part, and we allowed it to use more iterations for this decomposition step. But basically, you can see that once we just give our method like a little bit more power, like our method with 0 power just corresponds to the baseline, because it's doing like a 0 rank approximation to the variance. So it's basically just propagating the mean through, which is what the baseline does as well. But given a little more power, it already performs the same as using a lot of samples. And we did similar experiments on some regression data sets. This is the Boston houses classical data set, infamous data set maybe now. And when we trained, so okay, remember actually I said in the beginning I was just going to explain the dropout method for probabilistic neural networks. That was for this talk. So for the actual work, we also implemented like the more advanced Bayesian neural networks, and we can also use all of this stuff in Favour also works on those. And you can see in this case, I would say in this case, there's a little bit less. We don't do quite as well in comparison, I would say. By the time that we're able to match the samplings, like when we give ourselves enough time to match the sampling is already doing as good as us, at least on the 10 dropout one. I would say we could optimize our methods more, but at least for now, this is what it looks like. However, it depends a lot on the data set. So in this other regression data set where the output is 2-dimensional, we see a huge win. So in the Boston data set, you're just trying to predict the value of a house, I think. So it's a 1-dimensional output. But this one, in the energy one, it's a 2-dimensional output. And that means that sample-based method needs a lot more samples to sort of span the space and really get an idea of the uncertainty in different directions, where we kind of get that for free, both in the calibration plots and really all of the plots. We just have a really big advantage nearly from the beginning. So let me just quickly mention some things that I didn't have time to mention. One is convolutions, softmax, max pooling, which are all important components in neural networks. I would say maybe this is the biggest problem with our technique, is that each kind of neural network component requires handling specifically to really work well. We can always, of course, drop back to using samples for part of the network and then measuring the samples back to a variance matrix and then use Favour again, like do some sort of hybrid method. But if we really want to take advantage of this new technique, we need to think about each component individually. And if you want to know how we did each of those, you're welcome to ask me. The next step for Favour, like we believe that even on this Boston-Harting dataset, we should be able to outperform the sampling methods. But the nice thing about the sampling method is it's very simple. You just copy the thing and then you send everything to the graphics card. Whereas in our method, we have a lot of Python code and it's jumping in and out. And we think that if we actually were to write all of this in an optimized way, sort of fusing all the calls to CUDA and so on, we could make it much faster. But see about that. And of course, yeah, we could do bigger experiments. We really like this idea of using this diagonal plus low rank approximation to covariances, and we think it could be useful for a lot of other topics in Bayesian modeling and various things. So it would be cool if anyone has good ideas that they reached out to us. And this actually brings me to my last point. I just wanted to talk a little bit about the machine learning efficiency and like say why you should bring your problems to us and come and work with us on interesting ideas. We have a lot of areas we work on: algorithms, machine learning architectures, optimization, so any sort of thing that has any sort of relation to efficiency. We have various competences you might be able to use, and you're always welcome to ask anything. We've been working with the various groups, XFN groups, the CoAD, the Pandora group, as this works, of the AI for AI. So yeah, really just ping us if you want to explore opportunities. Thank you for listening to my talk, and see you around.